Anyway, as for now, we want to take a look at task 48, weak numbers. So what's it asking us? We define the weakness of number x as the number of positive integers smaller than x that have more divisors than x. Okay, so right off the bat, this is pretty loaded. There's a lot of stuff going on right in this first line over here. So we're talking about the weakness of a number. Now, I don't know if this is something that's like, that's commonly used in math or whatever else, but the point is, I wasn't aware of this concept until this problem. So this might be something that's like a fairly common thing. It might just be unique to what we're looking at over here. I'm not really sure, but either way, I found that this problem was a little tricky just because you sort of have to keep like multiple levels of info in mind. So I would find that I'd start writing an algorithm and then I'd get sort of confused between the divisors and the weakness. Anyway, maybe you'll see what I mean as we continue here, so we might as well do that. So basically, just to sort of unpack this first line over here, so the weakness of a number x, it's the number of positive integers, so like whole numbers, you know, like 1, 2, 3, 4, smaller than x, that have more divisors than x. So when we're talking about a divisor, we're talking about something that divides evenly into another number. So for example, if we're talking about 6, its divisors would be 1, 2, 3, and 6, because we can divide by those. We can't divide by 4, or we could, but we'd have a remainder, okay? So we wouldn't say that it divides evenly into 6. Okay, so basically the idea is we're looking at the number of divisors. And another really, really important note here, an important piece of information, we're talking just divisors, not prime divisors or anything like that. We're talking divisors. So we're going to make a distinction between those two pretty soon. But for now, let's continue with this. So it follows that the weaker the number, the greater overall weakness it has. That's kind of a strange sentence. I mean, that seems a bit tautological, but anyway, for the given integer n, you need to answer two questions. First, what is the weakness of the weakest numbers in the range from 1 to n? And it's an inclusive range. We can tell that from the square brackets around it. 2, how many numbers in the range 1 to n have this weakness? Okay, and then we want to return the answer as an array of 2 elements, where the first element is the answer to the first question, and the second element is the answer to the second question. Okay, great. So like we said, an example is worth a million words, so let's take a look at the example over here. Basically, they're saying, in this case, n is 9, which means that we're looking at the range of numbers from 1 to 9, inclusive, right? So including 1, including 9. Okay, so looking at those, basically, we first, let's try to sort of highlight the column here. We first get all the divisors. So like, for example, 1, it can only be divided by 1. 2, it can be divided by 1 or 2. 3 can be divided by 1 or 3. 4 can be divided by 1, 2, or 4. So it has 3 divisors. So we look at this and we say, well, so far, none of these numbers we haven't had any ones where the number of divisors is greater in a smaller number. Let me explain what I mean by that. So if we look at 5 over here, notice the number of divisors is 2, but there's actually a smaller number, specifically 4, that has more divisors than that. That's the only one though, so there's only one smaller number with more divisors. So we'd say that the weakness in this case is 1. If we go down to, okay, well actually at this point, our answer would be something like this. Like if it stopped there, if we were just looking at 5, like if n was 5, let's say, then it would stop there. We'd just say 1, 1, because the greatest weakness we found is 1. How many of them had that weakness? Oh, just 1 of them. But the thing is, if we were to continue, we find that 6 has 4 divisors. 8 also has 4 divisors. By the time we get to 9, we're looking at 9 and we say, oh, well, this has 3 divisors, but there are actually 2 numbers that are smaller than 9 that have 4 divisors. So that means the weakness would be 2, and there are 2 of them. Okay, so I should probably mention these two numbers are not always going to be the same. Like, for example, if we were looking at 7, if n was 7, then our answer would be like 2, yeah, weakness of 2. How many of them are there? Just 1. So they might not be the same number for the first and second. Okay, cool. So that's basically what we want to do. And note the guaranteed constraint. This is kind of important. N can only be as great as 1,000. So that sort of makes things easier for us, and we might take advantage of that guaranteed constraint as we continue with the problem here. So speaking of which, we should probably do some stuff. We should probably actually write some code here, make an algorithm. So what do we want to do with this one? Well, I'm thinking, like some of the previous ones, we probably want to break this down into functions. You know, we probably want to have like a function that's going to find the number of divisors, a function that's going to find the weakness, and then, you know, we'll find the maximum from there, sort of thing. Okay, so we'll start with that. So function. What should we call it? Num divisors, like how many divisors we have? Yeah, something like that. Okay, for a number, which we'll call num for now. We want to do this just pretty brute force for now. We're going to refine some of these algorithms, make them better as we continue, but for now, let's just make it pretty straightforward. So we're just going to say let how many be assigned the value of 0, and ultimately this is the thing we're going to be returning at the end, so we might as well just get that in there. And in the meantime, in the middle here, sorry, we're going to do something like this. So whoops, that's not the kind of nested for loop we want. So let's say d is 2. Okay, so actually wait, let's say d is 1 for now. Can it be divided by 1? We should probably check. And d is going to be less than or equal to the actual number here, num. All right, d++, because we want to go through all of these. And then basically we'll just say if num mod d is 0, if we could divide it by d and have a remainder of 0, then we're going to say how many plus plus. We've got a divisor. We don't need to know exactly what the divisor is. If we did need to know that, then we'd do something, you know, like divisors.push d or something like that, right? But we don't need to know what they are. We just need to know how many of them there are. So that's kind of an interesting aspect of this question, and that might allow us to do some kind of interesting stuff, actually. Anyway, as for now, let's see if this works. So let's just say return num divisors of, let's say 6, and we're expecting 4 for this one? Yeah, 4. Whereas if we were to put in 1, it should just be 1. Great, and let's try 10. Actually, I don't know, is that gonna be 4 also? Yeah, 1, 2, 5, 10. Okay, great. So we could even do something like this. We could do like Array.from, make a new array that has a length of 10, let's say, and it's gonna say for every element and its index, we want the element inside the array to be the number of divisors that we would have if we were to increase the index by 1, because we want to start this at 1 and not at 0, because if we started at 0, some weird stuff would happen. Okay, cool. So that looks about right, I think, right? We've got 1, 2, 2, 3, 2, 4, 2, 4, 3, and then we have another 4 at the end here because we went one further. So, okay, cool. That's pretty good, right? That's giving us our divisors here. So we can get the number of divisors for any element. Okay, how are we going to get the weakness of an element then? So function, let's say weakness, or get weakness. Let's do it the rainbow sprinkle style. Get weakness. Okay, of a number. So what do we want to do with this? Well, basically we want to find the number of divisors that this number has. So const divisors, or yeah, divisors. I'll call it that for now. And it's going to be the number of divisors that this number has. Okay, so we're going to start with that. And then from there, basically we're going to do something like this. So we're going to compare to this one. We'll say, actually, we need another one of these. How many? No, wait. Yeah, how many, right? Or let's just call it weakness, I guess. Yeah, weakness will start as 0. And we want to return the weakness at the end here. But what do we actually want to do with it? So basically what we want to do is start with numbers beginning at 1 that are strictly less than this number. And we want to keep this going, yeah, basically until we get right under the number we're looking for, because we're looking for how many numbers that are strictly below it have a number of divisors that are greater than this. So we'll say if num divisors of I is greater than divisors, then weakness plus plus, right? Does that work? Let's see. Return weakness. Weakness? No, get weakness. Get weakness of 9, let's say. And that should be what, 2? Let's see. It's 2. Okay, what about 8? That should be 0. Do we get a 0? We get a 0. Okay, so this looks like it's working. It looks pretty good. Are we going to get a 1 when we do the 5 here? Yeah, we're getting the 1. Okay, so if all we were looking for was just the weakness, then we could do something like this. Get weakness. And there we go, right? I mean, okay. Or, well, actually, I don't think that would totally answer it, because the weakness of the last number in the range is not necessarily going to be the greatest weakness, as we see over here, right? So we have something with a greater weakness. Let's find out. Let's find out what that is. So let's, since we need more than just this last number here, since we need more than just the last one, we need to sort of work up to that. So let's make an array full of weaknesses, okay? So we'll say const weaknesses. That's getting complicated, but anyway, Array.from. And we're going to give it a length of, well, here's the thing. We want it to start at 1 and go all the way up to n, which means, I guess it should have a length of n, right? Yeah, I think so. Yeah, because we're going to start it at 1. So we'll say x and I, x being the element itself, which starts as null, and then I being the index of that element. Okay, so what do we want to get from this? Well, we want the weakness of I plus 1. And let's not forget the word get in front of that. Okay, why I plus 1? Because we don't want it to start at 0. And when we do an array.from, naturally the index is going to start at 0, so we want to increase that by 1. So that's weaknesses. Let's just return that for now, I guess. Return weaknesses. And Rainbow says, I did this kind of sloppy. Yeah, well, I mean, I would consider what I'm doing right now kind of sloppy as well. So don't worry about it. We'll make it better. Okay, cool. So there's our weaknesses. Now, what else do we want from that? Let's say const max weakness is going to be math.max of weaknesses. Yeah, something like that, right? And then from there, we'll say const how many? We could be more specific than that, but this is fine. I mean, you might be thinking, whoa, hold on. You've already used how many. But yeah, I used it up here inside of another function. So this down here didn't have access. This how many up here was not within the scope of what we have over here. So don't worry about it. Okay, how many is going to be all the ones from weaknesses. So we'll do weaknesses dot filter. And we're going to find how many of these were actually equal to our max weakness. So maybe I'll just call it W. Yeah. W is the same as max weakness. Okay. Yeah. So then what are we wanting to return? Well, basically the max weakness. And how many? Let's see if that works. No, it didn't, because the way this filter is working is it's saying, okay, you want me to grab all the ones that are equal to max weakness? Okay, well, the 2 is equal to max weakness, and this other 2 is also equal to max weakness. In this case, just this 0 was equal to max weakness. Over here, both of these zeros were equal to max weakness. I want to find like a better example. Yeah, all of these zeros were equal to max weakness. So I think maybe you're getting the point. We don't want the actual array of all these things. We want the length of it. So I'm just going to throw a little dot length on the end there. We're going to run this again. And oh, you got to like that. Okay, cool. So let's try submitting that official. We'll see if it passes all the hidden tests. My only concern, okay, great. My only concern was that it was maybe going to time out, because if you think about it, we're not really doing this in a very efficient way. Like, we're finding the number of divisors in what I think is probably the slowest way possible. We're going through every single divisor and trying to find, you know, does it divide in? No? Oh, okay. Does this one divide in? Yeah? Okay, great. You know, like we're brute forcing this. We're brute forcing this. And every time we want to get a weakness, we're going all the way back to the beginning. We're calculating a num divisors for every single step there. When we do weaknesses, we're calling this function n many times. So we've got n, right? like big O of n just by doing this. But then the fact that this also has this loop in it makes it big O of n squared, or at least more like it. And then the fact that this is calling num divisors and this has this for loop in it means it's pretty much like a big O of n cubed, which is why I was starting to get a bit worried when I saw the 1000 here, because if we cube that, then it's a billion. That's getting pretty close to timeout territory. So, and not to mention the fact that, like, when we do each of these lines over here, both of these commands are going through the entire weakness array, like this one just to find the maximum, this one to filter it out. So we could make this a lot better. How are we going to do that? Great question. So first of all, let's cut this. Let's reset it. We'll confirm that. We'll paste it down here. We're going to give this a special name so it doesn't continue to run. We're going to do a test run to make sure we're getting a null, and everything looks like it's all in place. So let's do something a little bit different. So the first thing that I want to do, the first change I want to make is I don't like the fact that we're coming up with this weaknesses array, well, that we have this like weakness function that we're calculating individually, and then we've got this weaknesses array, and then we're manipulating that. So basically, I want to make a change. Yeah, I want to make a change. So specifically, how are we going to do this? Well, I think what I want to do is just to calculate the weakness, I just want it to be like, I was going to say like one loop. I guess technically it needs to be like a nested loop. Yeah, let's give that a try. So from here, yeah, actually all of this stuff, yeah, we're going to try to redo all of this. So we'll keep this the same for now. We will change it eventually. In fact, we'll change it in kind of a cool way. So look forward to that. But for now, we're going to do something different. So anyway, specifically, what are we going to do? Well, we want to get the weaknesses, but something to notice is that I have this array of weaknesses, right? The only time I'm actually using that array is to get the max weakness and to find how many there are. But I'm thinking, as we're calculating the weakness of every number, couldn't we just along the way say like, well, have we seen a weakness this big yet? And if we haven't, then we say, oh, well, now that's the maximum weakness, you know, like find it along the way. And if we have seen one that big before, we'd say, oh, well, then how many plus plus, right? Or if not, then don't do anything. But the point is, instead of doing like a get weakness, you know, calculating all these, and then after the fact trying to find like, well, which one was the biggest? Why don't we just pay attention to that as they go by? You know, it's kind of like, imagine you're on like an assembly line, you know, you got the conveyor belt and you've got a bunch of little samples and you want to see which one is the biggest. Well, would you just wait for them to all go by, fall into a bag, and then try to sort through the bag to find the biggest one? Why not just make a note of which one is biggest as you see it go by? So that's kind of the parallel I want to draw to this one. So we could do something like this. For let num, yeah, we've only used num up here, so this is fine. Let num be assigned the value of 1. That's where we wanted to start, right? Num is less than or equal to n. It's got to go all the way up to n, and num plus plus, okay? So we're going to run this. What are we going to do with this? Well, basically, we want to find the weakness of this number. Okay, so find the weakness of this number. And then we want to see if it's equal to the max weakness. And then after that, actually, hold on. Yeah, after that, then see if it's bigger than the max weakness. Yeah, that's basically it, right? Find the weakness. Yeah, I think that makes sense. And now that I'm thinking about it, maybe I didn't have to, you know, delete this over here. Yeah, that's probably going to be about the same. I don't think we're actually really going to make a change to how we're finding that weakness. Or are we? Let's see. Yeah, I don't think we're making a change to how we're actually finding the weakness. So, okay, const weakness is assigned the value of get weakness of num. Okay, great. And then before we even start this, let's just say let max weakness be assigned the value of 0, and let weak count, let's say. We assign the value 0. Okay, cool. So our weakness is this. See if it's equal to the maximum weakness. So if weakness is equal to max weakness, well, then we're just going to say weak count plus plus. And otherwise, we'll say if weakness is greater than max weakness. Well, in that case, we're gonna have to make a couple changes. First of all, we have to say that max weakness is now weakness. Yeah, cool. And then we also have to say that weak count is gonna be assigned the value of 1, okay? Because we found our maximum weakness now, but we only have 1 of it, right? Like, we might be going through the example and saying like, actually bad example, because, you know, well, no, not a bad example, because we're going through here, max weakness is like 0, 0, 0, and then we get to this point and it's 1. So we say, actually, hold on, sorry. We get to this point and we say, well, the max weakness is 0. How many of them are there? There are 4 of them. Whereas then the next one we say, oh, well, now the max weakness is 1, but we've only seen 1 of those, okay? So that's why we need to reset the how many, the weak count, okay? So we got that, and is that enough? Let's see. Return max weakness and weak count. Does that work? Hey, yeah, it works. Imagine that. Okay, neat. That's cool. Yeah, that's cool. Okay, good job. We'll try submitting that one. It's correct. All right, great. So we've got a couple other things we want to change here. So first of all, yeah, I like this. I think it's a lot nicer than like getting the array and then going through it afterwards. I think this just makes a little more sense. But I think we could probably modify it as well. We could probably change it again. So we're going to modify, I think, this part, and including the get weakness part. I think we're going to modify that. Yeah, I think we're going to modify that. So we'll do that eventually. But before we do, I actually want to modify this first. Yeah, so we've got our number of divisors. I want to talk about this for a minute, because there are basically 2 ways we could sort of look at this. So let's say we've got a number and it's 12. Okay. We all know and love the number 12. It's a great one. So we could say that 12 is equal to, I don't know, 3 times 4, right? So that means 3 and 4 are both divisors of 12. But they're not the only divisors. So when we're talking about divisors, it's not just 2 numbers that are going to multiply to 12. It's any number that could be multiplied by some whole number to give 12. So we've got 1, we've got 2, we've got 3, we've got 4, we've got 6, and we've got 12. So we have 12 divisors in total here. There's kind of another way we could look at it. So we could also do one of these factor trees that we've seen before. So we could say 3 and 4, right? 3 times 4 is 12. At this point, we could say, well, the 3, that's looking prime. So we're not going to go any further. Prime meaning, you know, it doesn't have any other divisors aside from 1 in itself. Whereas 4 can be expressed as 2 times 2. And both those 2's are now prime. So we can't go any further than that. We've reached the leaves of our tree. So we could say that 12 is basically, it's 2 times 2 times 3. Its prime factors are 2, 2, and 3. So then if it only has these prime factors, the prime factors are 2, 2, and 3, yet the total factors, like all the divisors, are 1, 2, 3, 4, 6, and 12. Well, how would we get these? How would we get these? Well, here's one way we can think about it. I think this is going to be kind of neat, especially for a guy, Rainbow Sprinkles, in the chat who loves binary numbers. So check this out. We've got 2, 2, and 3, right? And we want to basically form other divisors from this. So we could say, all right, well, let's say we don't want this 2, we don't want this 2, and we don't want this 3. Well, then our divisor is just going to be 1. We start with 1, we're multiplying it by not 2, and not 3. So yeah, we just get 1. Now let's say maybe I want this 2, but not that 2, and not that 3. So now our divisor is going to be 2. Okay, great. Now let's say I don't want that 2. I do want this 2, and I don't want that 3. Well, now it's just going to be 2 again, so let's actually skip that one. So instead, we'll say, I don't want that 2 either, but I do want this 3. And then we get 3 over here. We could say I want both of the 2's and not the 3, and that'll give us a 4. We could say I want one of the 2's and one of the 3's, that'll give us 6. Or we could say I want it all. I want all of these. And that gives us 12. So notice that the same divisors we have up here are the ones that we're getting over here just by multiplying combinations of our prime divisors. But here's the thing. If we look at these, we're kind of skipping some of these. We're skipping any of the situations where we'd have like just this 2 instead of just this 2. And that's because the order doesn't matter here. So there's actually a different way we could think about this. So I'm going to use my eraser tool, actually a bigger eraser tool, just for a second over here. Hey, it's got to be bigger than that. Okay, so it's a little better. And in fact, I'm going to delete all this as well. So check it out. This is a different way I want to think about it. Now we won't have just, we won't have both 2's. We'll just have one of them. And furthermore, we're going to limit this. Well, we're going to have different numbers here. So basically we're going to say, this is if we don't have any 2's and we don't have any 3's. This is 1, 2, and 1, 3. This is 1, 2, and no 3's. This is no 2's, 1, 3. This is 2 2's. Okay, this is 1, 2, and 1, 3. And this is 2 2's and 1, 3. Okay, so basically the idea here is that, oh yeah, and other than 1, can you loop up to half? Yeah, we could just make this go up to half the number, like num divided by 2, and then just assume that how many starts at 1, because of course every number is divisible by itself. Yeah, that is going to change for 1 because we don't want to double count the 1 in that case. So yeah, good point. We could, yeah, 1 would be an exception. Well, we're going to do it in a different way than that entirely. We're going to do it in a way that involves prime divisors. So something to notice here is that we basically had 3 options over here and we had 2 options over here, right? So, and maybe I should like even order these better, because if you think about it, like we've got 0, 0, 0 and 0, 1, 2, and then we've got 1, 1, 1 and 0, 1, 2. So basically the idea is that every one of these divisors is going to be some unique combination of prime divisors. And it's a combination, so order doesn't matter. Keep that in mind. So basically, if we want the total number of divisors, and there are 6, right? Number of them, it's 6. So basically, if we want how many there are going to be, well, basically we'll say for the 2's, since there are 2 of them, we could either have 0, 1, or 2 of those. For the 3's, since there's just 1 of those, we could have 0 or 1. So in other words, we have 3 choices here. We have 2 choices here. When we multiply these together, we get 6 choices. Okay, cool. So if we know the prime divisors, well, that's really useful because we just add 1 to it and multiply it by the total amount here. We could look at another example if you want. We could say, something more complicated. Maybe we'll make it like, well, does anyone have any suggestions? I'll just go with 360 for now, but if anyone has another suggestion, I'm open to it. So for 360, we could say it's like 4 times 90, I guess. Yeah, that works. 4 is 2 times 2. Oh, 256 I don't think would be all that interesting. It would just be a whole bunch of 2's, my man. We could do it, though. So we got 90, which would be what? We could say it's like 30 times 3. Yeah, I probably could have distributed that a little better. 30 is going to be 15 times 2. And 15 is going to be 3 times 5. Okay, really cutting it close at the bottom there, but we made it. So we got a 2. We've got another 2. We actually have 3 2's. And we've got 2 3's. Whoops. Yeah, there we go. And we've got 1 5. But you know what? It's actually not really that important what these numbers are. What we need to know is we've got 3 2's. Because we have 3 2's, well, it could be either 0, 1, 2, or 3 of these that we include. So that's 4 choices. We multiply that by, well, how many choices for 3's do we have? we have either 0, 1, or 2 of these. So we multiply by 3. And then for the 5, we could either include it or not include it. So we'll multiply that by 2. So we have 4 times 3, just 12 times 2. We're going to have 24 factors. So do we get 24 factors from 360? Let me zoom out, I guess. Let's try to list them. This might be a very bad idea. But anyway, let's try to list them. So we've got 1, we've got 2, we've got 3, we've got 4, we've got 5, we've got 6. Now, right off the bat, this is actually part of the reason. Fun fact for you guys, okay? If ever anyone here was wondering why there are 360 degrees in a circle, why there are 60 minutes in an hour, honestly, the reason is because this number has a lot of factors. We can divide it up in a lot of different ways, right? So it's like, you know, on a clock, the fact that we have 60 minutes as opposed to, like, let's say you wanted to make it metric time where it was like 100 minutes in an hour or something like that. Well, it'd be a bit awkward because instead of being like, oh yeah, I'll see you in 10 minutes, you'd be like, oh, I'll see you in 16.667. You know, it's a little more awkward that way. So anyway, 360 has a whole bunch of factors. So we got 1, 2, 3, 4, 5, 6. I don't think 7 is going to go in, but we do have 8, we do have 9, we do have 10, we don't have 11, we do have 12, we do have 15. I think we have 18. But do we? Well, 18 is what, 6 times 3? So yeah, we have 18. Yeah, we could do it that way, I guess. At this point, it's getting a little fuzzy for me. Would 24 work? Yeah, it would, because it's 4 times 3 times 2. Hopefully I didn't skip any in there. 24, I don't think 32, no, 32 is a power 2, that won't be possible, but 36 will definitely work, because times 10. I'm missing still 10 more of these. So, oh, yeah, I skipped 20. All right, I'll just put 20 over here. Okay, thanks. Thanks, Rainbow. Appreciate it. Okay, what else? What else am I missing? I guess I could just sort of think about it at this point. Like, we're halfway through, so we can just think about it in terms of, like, the opposite, right? So we'd say 360 would multiply by 1. 180 would multiply by 2. What would multiply by 3 to give us 360? 120, I guess. By 4, we'd have 95, what, 72? Yeah, 72. And then if we want to multiply by 6, wait a minute. Yeah. So it would be 60, I guess. Yeah, 60. If we wanted to multiply by 8, that's a tougher one. For 9, it would be 40, right? So we'll get that in there. So we're just missing 1. Okay, so it's this magic number. What is it going to be? Like 54 or something like that? I have a feeling it's probably 54, but let's see. 8 is basically just these 3 2s, right? So what are we left with? 9 times 5. Oh, 45, not 54. My mistake. Okay, so how many do we have here? We've got 6 plus 7 plus 5 plus 5. Wait, did I do it wrong? Oh no, did I miss one or something? I don't know. Or maybe this is wrong, because I think I only have 23 listed here, unless I'm counting wrong. I can't tell. But yeah, 1 and 360, 2 and 180, 3 and 120. You know what? Let's just verify it this way. So we've got num divisors, right? Let's just say return num divisors of 360. Why didn't I just think of that earlier? Oh my god. Okay, so it's 24. Okay, so we were right. So that tells us that what we're doing here is making sense, right? If we take the number of prime divisors, add 1 to it, and multiply it by the sort of total number here, then that should work. So we're going to make a new algorithm to sort of represent that. So let's get these guys out of here. We'll reset this and paste it in. Okay, cool. Oh, is it 15? Is that the one I was missing? Yeah, what does 15 pair with? Let's see. So 90 would multiply. Is it 16? Oh, wait. Is that it? No. Is it? No. Okay, so 15 times 2 is 30. So 15 times 6 is 90. 90 times 4. So it'd be 6 times 4. It'd be 24, right? Yeah, so it'd be 15 and 20. I don't know which one I'm missing. It's one of them, but anyway. Okay, let's go back to this. I think we'll keep most of this the same. Yeah, and let's not forget to put a little 2 on that. So let's paste that in. We'll keep most of this the same, but this, it's got to change. So how many is actually going to start at 1 now? D is going to start at 2. And we're actually going to keep this the same, but we're going to modify num as we go through. So basically, we'll do something like this. We'll say let additional or something like that be assigned the value of 1. Okay. And at the end of each of these, we're going to say how many is going to get multiplied by additional. That's going to be the idea. Now, instead of this over here, we're going to do this differently. So instead, we're going to say while num mod d is 0. While it's 0, well, we're going to say, first of all, if you can be divided by d, then divide by d. Actually do it, right? And also additional, it's going to get plus plus. Okay, cool. So then at the end of this, we're going to return how many. So does this work? Let's see. I mean, everything else is the same. So if it does work, it should just solve the problem. And it solved the problem. Okay, great. So that's nice. That's another way of doing it. I think that's going to pass all the hiddens. And I think that this method here, that this strategy would be faster. I'm thinking. Now you might be looking at that and thinking, well, 0. I don't know about that, man. You've got nested loops here. Wouldn't that be like an n squared situation? And yeah, good point, as opposed to this one here, which does not have nested loops. But here's the thing. So for this one over here, this the previous one we were using, let's say our number is 360. So this is going to go right from 1 to 360. This will execute 360 times. Okay, what about this one down here, or up here? So, well, yeah, you could say, well, it's going all the way to num as well. So if num is 360, it's going to go all the way up to that. But here's the thing. This one is dividing out everything it can at every step. So D is not going to get to 360 because num keeps shrinking. So basically, it's only going to be able to get as big. D is only going to be able to get as high as the biggest prime divisor that we have, which in this case is 5. So compare that to what we had downstairs. Even though these are nested loops, the one down here is going to execute 360 times, whereas this one is going to execute 5 times. And then you might say, yeah, okay, but for each execution, this is going to go a bunch of times too, right? Well, not really, to be honest. It's going to execute 3 times here. It's going to execute 2 times here. It's going to execute 1 time here. So basically 6 times total. So we got 6 repetitions plus 5 repetitions. That's 11. Compare 11 to 360. Oh my God. That is a huge, like not even comparable, like huge difference, okay? So even though this one looks more complicated, even though it looks like, well, you've got nested loops now, so that must be trouble, right? It actually will get the job done faster. So recommend this strategy is what I'm doing. Anyway, the point is I recommend this. That's what I'm trying to say. So, okay, this is an improvement. This is good. Have to head out a little early. It's you. Yeah, I'll be on tomorrow, ATD. I'll see you then, my man. Thanks for tuning in and have a great night. It might be a little early tomorrow, by the way, but yeah, we'll see. Anyway, see you then. Okay, continuing with this, I know we just came up with this really amazing way of getting our number of divisors here, and we're really excited about it, and it's like really setting us free, but I'm going to do it differently. Sorry. So, here's what we can do. Basically, yeah, I guess similarly, we'll take all of this, we'll try it again, and what do we want to change this to? Yeah, we're up to 2, so we'll make this one 3, and we'll paste this in. Yeah, okay, so that I think should just run normal at this point. Yeah, cool. So, okay, here's what we want to do. we want to find the number of divisors for each of our numbers. At that point afterwards, we want to find the weaknesses for each of our numbers. None of this is really surprising. It's what we've been doing the whole time. But we're going to modify both of the ways we do those, or the way we do both of those. So basically, first, we're going to change this. Okay, we're going to change our number of divisors. Actually, we're going to completely, radically change this entirely. Okay, so instead of getting number of divisors, instead of calling this on the fly, we're just going to get all the ones we need in an array, and then we're just going to reference that array. So maybe not as good for memory, but probably better for computation time because it means we won't have to run this loop every single time. Instead, what we're going to do is we're going to modify the strategy known as the Sieve of Eratosthenes. Okay, so Rainbow, I don't know if you took a look at my solution to your latest challenge, but I used one of those in there, I believe. Sieve of Eratosthenes. So if we take a look at this, hopefully there's an animation on this page. Yeah, okay, this is it. So we start by looping through the numbers. So we say, okay, start with just all the numbers here. We'll look at the first one, which is 2, and we'll just punch out all the multiples of 2 because those couldn't be prime. Then we'll take a look at 3. And that's the next prime one remaining that we haven't punched out. So we'll punch out all the multiples of 3, then punch out all the multiples of 5, punch out the multiples of whatever's next, which would be 7. We skip 6 because we know it's not prime. So only the gray ones are going to be our primes. And a lot of these are, you know, a lot of them don't remain after we go through. But anyway, the point is we get our primes by sort of like a process of elimination. We say, oh, well, any of the ones that are multiples of some other number, they are not going to be primes. So basically we go through them, we punch them out, we get rid of them. So we're going to use this strategy. This is a classic strategy for finding the primes, but we're not so much interested in finding the primes right now. What we're interested in is finding the number of divisors. And my claim is that this could be modified to do the same exact thing because prime numbers are really just ones whose number of divisors is 2, right? So we could do this in a more detailed way where instead of just punching out the numbers, we would actually like augment the numbers and give it a greater value at that point. So let's do that now. So instead of this, we're going to do our reverse sieve of Eratosthenes. And I think I horribly misspelled that. Eratosthenes. Yeah, and even the word sieve was misspelled. Anyway, okay, let's do that now. So basically, we're going to say let divisor count, I guess, be assigned the value of just this empty array. Actually, let's not make it an empty array. Let's make it a big full array. Let's give it 1,000 elements and fill them all with zeros. In fact, maybe we should, yeah, let's just put on an extra. 1001 for good luck. Anyway, the point is we'll go through this. We'll say for let D be assigned the value of 1. If D is less than or equal to 1000, yeah. Let's make a constant for that just in case we wanted to change it. We'll call it limit. It's going to be 1000 and this is going to be limit plus 1. Okay. And so then over here, this is going to go as far as the limit. Okay. Pushing it right to the limit here. Okay, plus plus. Great. So we want to go through each of these things, right? Each of our numbers. And we basically just want to say, okay, anything that's a multiple of this, it has this as a divisor. So basically, I'll do another loop for all of our multiples. Okay, so let m be assigned the value of 1. We want to keep this going as long as m times d is less than or equal to limit. And we want to do an m plus plus at the end of each of these. So what are we going to do here? Well, we're just going to say divisor count at m times d plus plus. That's it, right? I think that's all we need. And then let's just, for now, return divisor count, see what it's coming up with. So check it out. It's giving us our divisors. And if we take a look at this, we found for the first 9 divisors, it was 1, 2, 2, 3, 2, 4, 2, 4, 3. What do we have here? 1, 2, 2, 3, 2, 4, 2, 4, 3. I think it's right. Okay, so we're getting all of our divisors. And look, we get all of them. We didn't need to keep calling this same function. You know, we didn't need to say, okay, now let's get the divisor for this number. Okay, now let's get the divisors for this number. Now let's get the divisors for this number. Instead, we just say, oh, hey, how about we get the number of divisors for every one of the numbers? We do it all at once. And if we wanted this to be bigger, you know, let's say we wanted it to be 10,000. Then all I need to do is change this one thing. Hopefully it doesn't time out. No, it's not timing out. It's giving us all of these. The number of divisors for the first 10,000 numbers. Well, that's pretty good. I think that's pretty neat. So, okay, good stuff. We were able to use our Sieve of Eratosthenes to come up with this big divisors count. And you know what? This could be a constant, right? Because the binding is not going to change. It's going to be bound to this array no matter what. The contents of that array will change, but it's a constant binding. So important to keep in mind. Okay, so at this point, since we have all of this, well, actually we can get rid of divisor count over there. Now, all we have to do is this. So instead of num divisors at num, we can just say divisor count at num. And now this should work just the same. Oh, num divisors, where am I calling that? Oh, over here, okay. So divisor count at I. Yeah, okay, this, and now that works. Is this going on YouTube? Yeah, that's the plan. I realize I have a pretty significant backlog there, but yeah, it'll go up eventually. Why limit +1? You're talking about this part here, right? So the reason I'm making this +1 is because the array by default will include a 0th element, but I'm not interested in that 0th element. I don't need to know how many divisors 0 has, so we're skipping that one. But the reason I'm not just saying like, you know, make it limit and then just put like a -1 on everything is because then when we do this, like divisor count at num, we'd have to do like num -1, which would be a pain. So I want it to go all the way to 1,000, but I also want it to include 0 just to sort of offset the indices. So hopefully that makes sense. All right, so we've got a reverse sieve of Eratosthenes. It's giving us our divisor count. We can get that instantly, no problem. So that's working really nice. Now, I believe we can make one more modification here. I think we can change this one more time in such a way that's going to make it a little better. Yeah, maybe a little better. So, how are we going to do that? Well, basically, we're going to do something with this for our weaknesses. In fact, maybe I'll just delete some of this stuff over here. Yeah. Oof, that's intimidating. All we have is our reverse Sieve of Eratosthenes now. But okay, what do we want to do? So here's the thing, okay? I don't want to have to call our weakness function every single time. Yeah. Yeah. I don't want to have to call our weakness function every single time. So instead, I'm going to take advantage of the fact that we're going to work up from 1. Yeah. And we're going to keep this going until it's less than or equal to n. We'll do our num plus plus. This is what we had before, right? Okay. Now before we were, yeah, down here, right? Yeah, at this point. So before we were doing this, we were doing get weakness. But instead of that, I want to modify, you know what? A lot of this is going to be the same as what I want. So I'm just going to copy this. Okay. So here we go. Now it's in here that we're sort of missing weakness function. Okay, so just keep that in mind. I'm putting this here mainly as a note to myself so I can see, yeah, here's all the Sieve of Eratosthenes stuff. And then down here, we're missing the function that we're calling right here. So we're gonna have to handle this in a slightly different way. Okay, but we're gonna have max weakness. We're gonna have weak count. Those are going to be the same. We're not going to modify those. Okay, so then what else do we want? Well, okay, so I want to make this other thing. I guess I'll call it lesser divs, and it's going to be an object. So what are we going to do with this object? Well, okay. Basically, this is how it's going to work. Instead of saying, okay, hold on. Weakness represents the following, right? The weakness of a number is how many numbers that are smaller than it have more divisors than it, right? That's basically the idea. So what I want to do is for every number that we go by, so we've got the number 1, we'll say let divs, you know, divisors, be assigned the value of divisor count, I guess, right? Yeah, divisor count at num. So this is the number of divisors that it has. Okay, and then what I want to say from there is for let I be assigned the value of 2, let's say. I is less than divs I plus plus. I'm just gonna write this all down and then I'm gonna explain what's going on with this because it's gonna look a little complicated at first. We're gonna ask if this exists. If it does, then we're gonna add 1 to it, and if not, we're just gonna return 1. Yeah, we're gonna make that 1. Okay, cool. And then the way we're going to handle weakness down here is going to be a little bit different. But before we get into that, let's just talk about what this is. Okay, so divs, that's basically the divisor count of our current number. So maybe let's say, I don't know, our number is 5. So the divisor count is going to be 2. Actually, wait, let's say our number is 4. So the divisor count is going to be 3. So at this point, then we'd say something like, well, lesser divs at I, right? So lesser divs, in other words, how many lesser divisors are there for the number 4? And we'd say, well, does it exist already? And if it already exists, we're going to increment it by 1. And this is for everything from 2 to 4. Okay. And yeah, sorry. That my mistake. So what I was saying is if the number is 4, actually, I don't know if it's right to just dive into an example. Let's try. Okay, so if the number is 4, divisor count at 4, that was 3, so we get the 3 there. So divs is going to be 3. And then we say for let I be assigned the value of 2, I is less than 3. So basically this is only going to run once, and it's just for the I value of 2. And we say lesser divs at 2 is going to be assigned the value of the following. Well, does it exist, first of all? If it doesn't exist, then make it 1. If it does exist, then make it 1 greater than whatever it was. So what is lesser divs? It's the number of numbers that have that have more divisors than the current one, but are a smaller number than the current one. Right? Does that make sense? Let's think about it. So basically, if our number was 4, then we say we have a divisor of 3. Right? The number of divisors we have is 3. So what we're saying is for everything less than that, for 2, well, we're not keeping track of 1 and we'll find out why. But for everything less than that, we're incrementing the number by 1. So that the next time we get to 2, we say, oh, well, let's look up 2 in our lesser divs count. How many did we have that are of a lesser number, but have more divisors than this, more factors than this one? Well, 4 had more factors than this one, right? So we'd say, oh, okay, well, there's 1 in there. So I guess the weakness here is 1. So that's basically it. If we want our weakness, we no longer have to check this. We could just say it's going to be our lesser divs at num, is it going to be? Or no, sorry, not at nums, at divs, right? The number of divisors. Or if that doesn't exist, 0. Okay, so is this in a form where it's going to run? Yes, it is. I think this is probably the best way to do it. We don't need a weakness function, so we can delete that. I could be wrong. I could be totally way off base about this, but I kind of think this is the best way to do it. And the reason I say that is because well, this over here is going to be, I think, the most efficient way of calculating all of the divisors, all of the number of divisors for all of our 1,000 numbers here, because we don't have to call this 1,000 times. We basically have this nested loop here. Well, this ends up executing 1,000 times, yes, but how many times this executes gets smaller and smaller and smaller and smaller and smaller. And so the first time, yeah, it's going to be close to 1,000. The second time, it's already down to 500. After that, it's at about 300. So it's just going to drastically drop off. So this whole thing, coming up with the Sieve of Eratosthenes, I'm pretty sure, don't quote me, but I'm pretty sure this would be big O of n log n. I'm pretty sure this would be an n log n situation. As opposed to down here, we found that this one, the time complexity was not nearly as bad. It was probably something closer to linear than like a squared, but then we have to call it 1,000 times. So that's going to be squared, like quadratic complexity no matter what. So over here, we're keeping the complexity down. And then as we go through this, basically we just go from 1 to n. So again, that's just n, This would be big O of n, right? And in terms of what we're doing in here, notice we're not calling any functions in here. We're not calling, well, we haven't defined any other function, so there's nothing to call. So really, I mean, you could say like, well, technically you have a nested loop over here, but this loop is not gonna fire very many times. I mean, like, what's the biggest number of divisors you could have? I think the biggest one we've seen was like 12 or something like that. So if you have, or wait, no, sorry, 24, right? How could I forget? Anyway, so if it's 24, then this is going to fire, what, 22 times? Something like that. It's not that many. So I have a feeling that in total, this algorithm is probably about a big O of n log n, maybe worse complexity n squared, but I don't think it could even get to that. I'm pretty sure this is in the ballpark of an n log n. So I think this is probably the best solution we've got. The only part of this that I'm kind of feeling a bit iffy about, I guess, is this lesser divs thing. I mean, it makes sense, but it's kind of hard to explain. The idea is basically that since we know that this is going in order, since we know that it's going from 1 to n, you know how like weakness is all about how many numbers that are less than the current number have more divisors. Well, the way we're handling it here is we're saying, since we're incrementing from 1 to n, we know that whatever divisors we have now, whatever ones we're checking right now, later on, this is going to be a smaller number than every one of the numbers that we check after this, right? So basically, we can just say, well, necessarily the one we're looking at, if it has 4 divisors, then it's going to have more divisors than any number that follows that has either 3 divisors or 2 divisors. We know that nothing is going to have just 1 divisor, which is why I didn't bother putting in a 1 over here. It would be pointless. Okay, so that's basically the idea behind this. I guess we should check if it's going to pass the hidden tests. It would be really embarrassing if it didn't. Anyway, I think this could probably be a constant over here. I think this could be a constant. We'll just do a couple touch-ups, and then I think we'll be good to go. Let's see. Is that good? Hopefully that still works. Yeah, it still works. Okay. Yeah, all right, cool. I think that's the best one. Like I said, I'm pretty sure this would be like big O of n log n, which is coming a long way from like our big O of n cubed that we started with. So I think we've made a lot of good progress here. Yeah, we can probably wrap it up for now. So let's get out of here.